This video lesson corresponds to section 18.4 of your textbook on age dating with radioactivity. I call it radiochemical dating, and it's a little bit different from your text in that we'll go a little deeper into the mathematics because, after all, this is honors chemistry. So what is radiochemical dating? Basically, it's a method to determine the age of a radioactive object by assessing the amount of radioactive isotope that is remaining. That, of course, means you have to make the assumption of how much radioactive material was there at the beginning of the decay, so N sub O, or the original amount from our notes yesterday. The most well-known method of age dating something using radioisotopes is carbon-14 dating. Now, carbon dating is based on the beta decay of the radioactive isotope carbon-14, which is produced at a constant rate in the atmosphere, and it's because of the bombardment of nitrogen-14, which is the most stable isotope of nitrogen, bombardment by incoming solar radiation or cosmic rays. That's shown in this cartoon here. Basically, a nitrogen-14 is bombarded by an incoming neutron, and the neutron is captured by nitrogen-14, converting it to radioactive carbon-14. Now, that radioactive carbon-14 can become part of carbon dioxide, CO2, which is, of course, taken up by living plant matter during photosynthesis. Uses carbon dioxide as a reactant in the photosynthesis reaction that's converted to trees and leaves and bark and grass and all that sort of thing. So all plant matter has some level of carbon-14, which is, of course, eaten later by cute little bunnies and horses and deer, and so it's constantly replenished not only in plant tissue because of photosynthesis, but within living animals, because we, as well as horses and bunnies, eat plant matter all the time. Now, that's constantly replenished until we die or the plant dies, and then that carbon-14 is no longer replenished. So as soon as you or I start taking a dirt nap, the amount of carbon-14 begins to decay radioactively and becomes less and less abundant in the body. So back to notes here. The half-life of carbon-14 is 5,730 years. It's very accurately determined. And in living plants, and this is slightly variable from plant to plant, of course, but generally in living plants, trees, grass, etc., the activity is about 15 counts per minute, or decays per minute. So that is your original amount, N sub 0, which is a symbol you're used to seeing from yesterday's notes. Now, after death, recall, carbon-14 is not replaced anymore, so it begins to decay or continues to decay and becomes less abundant in the body. And so age dating is basically a comparison of the amount of existing carbon-14, which is N sub T, the amount remaining at time T, compared with an original amount, which we assume is 15 counts per minute for plant matter. And by comparing that ratio of existing versus original amount, we can figure out an age, or how old the material is. And so let me give you a couple of examples of how to, well, first, let me back up. You can solve the problem of how old a sample is based on this formula right here. Now, there are some symbols here you may not be familiar with. First of all, ln on the left, the natural log, ln. Now, I don't care if you know what the natural log is. It's an exponential function. What I do care is that you know where the button is on your calculator. And on your calculator, ln, natural log, is on the left-hand side, the far left, near the bottom, 3 buttons up from the bottom. And so the natural log, this formula is the natural log of the ratio, again, this should look familiar, the ratio of the amount remaining at any time t, that's N sub t, over N sub 0, the original amount, is equal to negative lambda times t. Now, t is elapsed time, and that's what you want to solve for if you are determining the age. But lambda is something different. So first of all, t is elapsed time. That, I think, is in a note in a second. But lambda is something you're unfamiliar with. Lambda is called the decay constant, and lambda is written like this. Here's a big lambda, and it is the decay constant, and I'll explain what that is in a second. So t is elapsed time, is age. That's what you want to solve for in this problem, is t. But lambda is this thing called a decay constant, and it is unique for every isotope. It's very closely related to the half-life, and you can calculate the lambda or decay constant based on this formula right here. Lambda is equal to 0.693, which is related to the natural log, 0.693 divided by the half-life. And so you can see that lambda would have some unusual units. Half-life would be in minutes or seconds or years, and so the units for lambda is the inverse of some time. Seconds, again, minutes, years, whatever it might be. So let me show you how you put these two formulas to work and solve a couple of age dating problems. So here's one. Pretend you are an archaeologist, and you've come across a fragment of a woven reed basket, let's say in a cliff or cave settlement in the desert Southwest. And you want to put an age on that artifact. So you take your woven basket sample, which is of course made of reeds or grasses, plant material, and you assess the amount of carbon-14 activity, and you find out that the existing carbon-14 activity is 9.2 counts per minute. So what is the age of the object? Well, you start off knowing some things. First of all, you did the assessment and you found out the amount remaining at time t, which is right now, the elapsed time, is 9.2 counts per minute. That was given in the problem statement. And you use the assumption that the original counts per minute in plant matter is 15 counts per minute, and you also know the half-life. The half-life of carbon-14 is 5,730. So now you need to solve the problem and substitute your values in for these variables, for the formula we just talked about on the previous page. The first thing you need to do, though, is solve for lambda, the decay constant. So you plug your values into this formula. Remember, lambda is 0.693 divided by the half-life, shown right here, and 0.693 divided by the half-life of carbon-14, 5,730 years, is this value. Pretty small number, 1.21 times 10 to the negative fourth per year. And basically that number represents the likelihood that any one isotope of carbon-14 will decay per year. So it's a pretty small number, and you can see that if the half-life is really large, if this number is really large, then lambda is going to be really small. So it's a small likelihood that any given atom would decay. Okay, back to the problem. Now it's an exercise in plugging and chugging. The natural log of the existing amount, 9.2 counts per minute over 15, is equal to negative lambda, and lambda in this case was 1.21 times 10 to the negative fourth per year, times t. And again, t is what you're solving for. Let me scroll down. So a quick note, first of all, it's very important that you conserve or you're careful about your signs, positive and negative signs here. Notice this negative sign right here, negative lambda, is really important because the natural log of any value less than 1, a fraction or a decimal, I should say, is always negative. And this ratio will always be smaller than 1, the amount remaining over the original amount. And so you'll have the natural log of some value will always be negative. That's shown here. So once I calculate the natural log of 9.2 over 15, I get negative 0.489. And notice you'll be dividing by, here's negative 0.489. You'll be dividing by another negative until you get a positive value. And the answer in this case is a little over 4,000 years, 4,040. And so this wicker basket or woven basket sample probably represents something from the Anasazi Indians, which were the very famous cliff-dwelling community 2,000 years before Christ, and it was quite a thriving culture. Let me do one more example for you. Here is an example from medical imaging. Carbon-11 is sometimes used in medical imaging. You can see it's got a very short half-life, 20.4 minutes. And let's say we dose a patient with about 5 milligrams of carbon-11. How much time would it take before the amount remaining in the body is less than 0.1 milligrams? Let's assume that's some safe level. Well, once again, we know some things. We know the amount remaining at time t, and that's 0.1 milligrams. So this is n sub t. We know the original amount is 5 milligrams. That's n sub 0. What we're trying to solve for is t. We don't know lambda yet, but again, we can solve for lambda pretty simply. Lambda is, once again, 0.693 divided by the half-life, shown there. So we plug those numbers in, and we get a value for lambda of 0.034 per minute. And then once again, plug and chug. Put your numbers in. The natural log of 0.1 over 5 is equal to negative 3.91. Again, be careful of that negative sign right there. And then you can solve for the amount of time, which is about 115 minutes, or just a shade under 2 hours until it's decayed to a safe level. And so that's all for this video lesson. I will send out a voice thread that solves another problem, and I will also include a website to see this video lesson again on YouTube if you want to have another look. Thanks.